today I would like to talk to you something different than in our earlier lectures. In our earlier lectures, we have been talking about waves that have been propagating through the volume of a plasma, and these could be electromagnetic waves, which are transverse waves like this. This is the direction of propagation, the electric field is transverse, or electrostatic waves, which could be longitudinal. So if they are traveling in this direction, then the electric field oscillates like this. But these waves were traveling inside a plasma, which is the bulk of the plasma. So these waves travel in this region. Well, they are also influenced by the boundaries, if the boundaries are closer to the wave propagation. However, the effect of boundary is not that significant on the character of these waves. Plasmas also support a particular kind of mode that travels on surface. So suppose I consider a boundary between a plasma and free space, and let me call the direction here as z, and this direction as normal direction as x. Then there is a possibility of a wave propagation along the surface, and this wave is sort of an electromagnetic wave, but it is a little complex structure that the electric field of the wave has a component in the direction of propagation as well as in the normal direction, and the amplitude of both components are maximum on the interface, on the surface separating the two media. Let me call this surface as x equal to 0. So this is a very particular kind of wave which influences, or which is influenced by the properties of the medium near the surface, and what happens in the near, far away from the surface is not that significant. Obviously this requires sharp boundaries. Such sharp boundary plasmas are difficult to form, to create in laboratory, but with tunnel ionization one can certainly create plasmas with very well defined boundaries. However, from the perspective of plasma physics, one can treat conductors, semiconductors, and even the soil as sort of a conducting medium. So any conducting medium which has finite electrical conductivity can support this kind of wave. Traditionally, it was during maybe 30s, 40s rather, when people were thinking of radio communication at medium frequency waves, people recognized that if Earth has a curvature like this, then and Earth has a finite conductivity which is non-zero, then medium frequency waves can travel as surface waves, and they can be guided by the curvature of the Earth. So as the Earth bends, they will also bend. And if there is a mountain somewhere here on the surface of the Earth, then these waves will climb the mountain and get down from the mountain. These are very special kind of waves which are primarily guided by the surface of the material, the surface of the conductor, maybe Earth in this case. And they could be very useful for radio communication. The reason is that if I have an antenna placed here, suppose I have an antenna placed here, if there were no Earth, these waves will be traveling in this direction, they will not bend. So they will travel as sky waves and they will hardly bend. But if there is a conductor here, are excited as a surface wave, then as the Earth bends, they can bend. And their propagation has been recorded up to distances of several thousand kilometers, and the attenuation is also not very large. So that is a beautiful example of surface wave being employed for communication. These waves are called surface waves in communication jargon, but in plasma physics they are known as surface plasma waves. In last 30 years, lot of interest has been generated on these waves, especially the waves propagating over the surface of a conductor like gold or silver and free space. So these waves are guided along the surface. They penetrate just very little, a fraction of a micron inside the conductor, and they extend a few microns in free space, and they are so much influenced by the presence of any contamination placed on the surface of the material that their propagation constant is influenced, and these can act as very good sensors. So there is a great advantage of employing these waves for sensor applications. I think before I delve into the applications, I would like to talk to you in some detail about the nature of these waves, how do they propagate, what is their phase velocity, what is their mode structure, and so on. So let me address the issue of surface wave as a guided wave. I am considering a conductor here. It could be a plasma, it could be a soil, or it could be a metal. I will call this as conductor or semiconductor, and characterize this by effective permittivity epsilon m. And this is free space here on top, and I will be characterizing this by a effective plasma conductivity permittivity like unity. And I will be using a coordinate system with this as my z-axis and vertical direction as x-axis. This is my x equal to 0 plane. You know, if I am talking of propagation of a wave of frequency omega, then conductor permittivity, effective permittivity is epsilon r plus I sigma upon omega epsilon 0, where epsilon is called the relative permittivity of the material of the conductor. For instance, epsilon r is 4 for silver, epsilon r is 9 for gold, 4 for silver, 9 for gold, and so on. Sigma is the conductivity, electrical conductivity. For earth, sigma is typically of the order of 1 unit in MKS units, 1. Epsilon 0 is free space permittivity, which is 10 to the power minus 9 upon 36 pi in MKS units. Sigma is the electrical conductivity. Now, in case of plasmas, this expression simplifies. Even conductor this simplifies if I put the expression for conductivity and ignore collisions, then epsilon m is equal to epsilon r minus omega p square over omega a square in conductor at high frequency. If collisions are ignored, if one includes collisions, then there is a factor here that can be multiplied. But a lot of interesting physics can be understood if I take this real expression for epsilon m. So now, first of all, let me develop a formalism, then we will put these actual expressions for epsilon m. One may certainly recognize that this quantity depends on frequency. Omega p is the plasma frequency, which is related to the density of the conductor. If it is there are free electrons there, then omega p is related to free electron density as Ne E square upon m epsilon 0 under the root. This is called the plasma frequency. Now let me consider the propagation of the wave. This is my interface with z-axis here, x axis there, x equal to 0 is the dividing plane. I will call this medium 1, medium number 2. And suppose this is my point z equal to 0. Rather, I will consider this z equal to 0 plane. When I look for wave propagation, I say that the electric field of this wave, which is traveling in the z direction, whatever is the field here at z equal to 0 at time t, suppose I choose that my electric field at z is equal to 0 at time t is sinusoidal of this form A exponential minus I omega t minus k, omega t, this is the sort of variation I am presuming. Suppose I consider the electric field of this wave to be having time dependence of this form. Actual electric field is the real part of this, means A cos omega t. And I say that the same field is appearing here at z position at a later time. My issue is that the field at z at time t, I would expect to be the same at E as E at z equal to 0 at a earlier time t minus the time signal takes to travel from z equal to 0 to z equal to z, and that is z by v phase, where v phase is the velocity of signal propagation. So if I put this in this expression, this becomes is equal to A exponential minus I omega t minus omega upon Vph into z. I use a symbol omega by Vph as kz. Conversely, I can say that the phase velocity of the wave is omega by kz. So if I use this signal, then I say that for a wave that propagates without distortion, because this field will have a r dependence also, xy dependence also. Same xy dependence is it here. If it is the same is reproduced here at a later time, then the field must have this sort of delayed response, and hence we assume that my electric field of this wave is written as some amplitude which is a function of x. Y dependence I neglect, saying that the field is uniform in y direction, exponential minus I omega t minus kzz. This sort of tz dependences guarantees that the wave is maintaining its x profile as it travels. The issue is that if my electric field depends on on x, amplitude depends on x, then it must satisfy the wave equation. Wave equation for the electromagnetic wave is del square E plus omega square by c square E equal to 0 in free space, and inside a medium, conductor medium is del square E plus omega square by c square epsilon m into E is equal to 0 in the conductor. This equation is true for x component of electric field as well as for z component of electric field. Let me write down this for z component of electric field. And then I say that del square is d2 dx square plus d2 dz square but we have already taken z dependence of the field whether in free space or in the conductor to have like this form. So, I will replace this delta delta z by ikz, and this becomes d2 dx square minus kz square. Because this has to operate over the electric field which has a z dependence of this form. So, this will become like this. So, let me write the field inside in the free space. It would be like d square Ez by delta x square minus kz square minus omega square by c square. Ez is equal to 0 in free space, and this is a constant quantity. So, I would define this as alpha 2 square is equal to kz square minus omega square by c square. Then this equation can be written as d2 Ez by delta x square minus alpha 2 square Ez is equal to 0, and the solution I can write down as Ez is equal to some constant, say A0, exponential of minus alpha 2 x, and this dependence is explicit. So, I have to write it exponential minus I omega t minus kzz. So, this is my electric field of this surface plasma wave in free space. A similar exercise I will do to solve this equation. Again replace here del square by this quantity like this. Then my equation for Ez in the lower medium would be inside the conductor I would have del square Ez by delta x square minus kz square minus omega square by c square epsilon m into Ez is equal to 0. I will call this quantity as alpha 2 square or alpha 1 square in the lower medium as kz square minus omega square by c square epsilon m. Please recognize that I am talking of this geometry. This is my z axis, x axis, x equal to 0, and this is medium number 1, this is medium number 2. Free space is above, metal or conductor is underneath. Solution of this equation can be written as, which behaves well correctly for x tending to minus infinity. The field should not go to infinity. It should be well behaved solution. Then this would be A0 dash, some constant, exponential of alpha 1 x exponential minus I omega t minus kzz. Please recognize this is for x less than 0. For x bigger than 0, my solution was Ez is equal to A0 exponential of minus alpha 2x exponential minus I omega t minus kzz. This was for x bigger than 0. A minus sign is written purposely so that when x goes to plus infinity above, then the field should not go to infinity, it should go to 0. This is a well behaved solution. Continuity demands that Ez is tangential, Ez is the this component of electric field. They should be continuous at this interface. So, continuity of Ez at x equal to 0, this is the interface. It demands says that A0 dash should be equal to A0. put x equal to 0 here, both everything is same except this. So, this is the quantity. However, to obtain Ex, either we solve the equation for Ex, or a easier way is that go to first Maxwell equation, which says that divergence of epsilon m into E is 0, where epsilon m is the effective material permittivity. For free space, this is unity. This is the important condition. Del operator we are taking to have only x and z components. So, this equation tells me, and epsilon m is a constant in a particular medium, whether you are considering free space or conductor. This is a constant, so you can take it out. So, this will be satisfied when divergence of E is 0. This equation implies delta delta x of Ex plus delta delta z of Ez equal to 0. Delta delta z I have already written as I minus as ikz. So, this tells you that delta Ex upon delta x is equal to minus ikz Ez. One can integrate this equation, and because the x dependence of this is exponential, this gives you straight away Ex is equal to, in the lower medium, this will give you minus ikz upon alpha 1, and then this will be a 0 exponential of alpha 1 x exponential minus I omega t minus kz z, and this is for x less than 0. For x bigger than 0, the same thing will integrate to give you, for x bigger than 0, this is equal to Ex is equal to ikz upon alpha 2 a0 exponential of minus alpha 2 x exponential minus I omega t minus kz z. Interesting part here is that at x equal to 0, this Ex is different than this Ex, they are not equal. Ex is, and the signs are also different, there is a phase difference of pi. Another important thing is that at the boundary, normal component of effective displacement vector should be continuous. At the boundary, which is x equal to 0, epsilon into E, x should be continuous. This is the effective relative permittivity of the medium multiplied by Ex, which is called the normal component of the displacement vector, should be continuous. In free space, the value is unity. So, I would say that Ex in the second medium should be equal to, in the first medium or lower medium, the value of this quantity is epsilon m into Ex in the first medium. If I use the earlier expression, I will find that at x equal to 0, every term is cancels out, except you will get 1 upon alpha 2 here is equal to minus 1 upon alpha 1 into epsilon m. Now, what you can do, and recognizing that alpha 1 is kz square minus omega square by c square epsilon m, and alpha 2, well, under root of this quantity, and alpha 2 is kz square minus omega square by c square under root. Recognizing this, we square both sides so that under root signs are removed, and this equation can be solved, and this gives you Kz is equal to omega by c into epsilon m upon 1 plus epsilon m to the power half. This is the dispersion relation for the surface plasma wave. But we recognize that if the field amplitude has to decay away from the interface, recognize that this is my interface, x equal to 0, and this is my x direction, vertical direction. If I want my field amplitude to fall off with x either in the upward direction or downward direction, then alpha 1 and alpha 2 should be real, or should have a large real part. This will happen only when Kz is bigger than this quantity, and Kz is bigger than omega by c also. So, what we are looking for, that Kz is bigger than this quantity. If I put the value of Kz in this expression, alpha 1 turns out to be equal to omega by c, square this, and you will get simply 1 upon 1 plus epsilon m to the power half. This is epsilon, 2. I am substituting this back here, and you will get this expression, which tells you if this quantity has to be real, minus 1 upon this quantity, this is minus here. Just substitute this value of Kz here in this expression, and this turns out to minus 1 upon this quantity in this expression. And how about Kz1, alpha 1? Alpha 1 turns out to be also a similar expression that I can write here. Alpha 1, the field decay in the conductor is omega by c, and it turns out to minus epsilon m square upon 1 plus epsilon m to the power half. It is a very strange kind of thing. If I want alpha 1 to be real, I must have this quantity to be positive. Epsilon m, even if it is negative, square of this quantity will be positive. So, there is already a negative sign in the numerator, and hence 1 plus epsilon m has to be negative. Only then alpha 1 will be real. And similarly alpha 2, let me rewrite this, alpha 2, which is equal to omega by c minus 1 upon 1 plus epsilon m to the power half. This is a very important thing, that this wave will travel along the surface only when wave travels only when 1 plus epsilon m is less than 1, less than 0. If I use the expression for epsilon m, which is equal to 1 plus epsilon r minus omega p square upon omega square has to be less than 0. This tells you that omega has to be less than omega p divided by under root of 1 plus epsilon r. For a gaseous plasma, epsilon r, the relative permittivity is unity. So, 1 plus 1 is 2. So, this becomes omega p upon root 2 for plasma. For conductor, epsilon r is different than 1, so this could be less than omega p by root 2. So, there is a limitation that the waves which have to travel as surface waves along the interface between two media, their frequency has to be below certain quantity, and this quantity is called surface plasmon resonance frequency. So, let me define this. Surface plasmon resonance frequency resonance denoted by a quantity omega r is equal to omega p upon under root of 1 plus epsilon r. If I plot kz versus omega using this expression, then please recognize kz I can explicitly write as omega by c, and this can be written as omega p square upon omega a square minus epsilon r divided by omega p square upon omega a square minus epsilon r plus 1 to the power half. And let me plot this. Normally people plot kz here and omega here. Then at omega equal to omega r, which is this frequency, what do I get? When this becomes equal to this, denominator becomes infinity, a 0, and kz goes to infinity. So the plot is, and like this becomes linear here and then goes like this. So this is a wave where kz, this quantity is bigger than 1, and kz could be quite large. So the phase velocity of this wave, which is omega by kz, is always less than c and could be much less than c. Now that makes this wave very, very interesting. Very important thing is about this wave is the diffraction. You know, diffraction of a wave is dependent on the wavelength of the wave. Longer the wavelength, stronger the diffraction, divergence of the wave. But this wave has a shorter, larger k and hence shorter wavelength for a given frequency, and hence suffers very little diffraction. You can focus this wave to a size much less than the wavelength in free space. That is the advantage of this wave, and that is why from device applications point of view, this wave is getting more and more attractive. Now let me tell you a few interesting things about this wave. First of all, this wave, if I plot electric field of the wave, which Ez for instance, modulus of this quantity as a function of x, if I plot x, I am plotting here. This is above the surface, this is below the surface of the boundary between conductor and free space. So the Ez is continuous, so this will fall off like this, exponentially fall off. In the conductor, this will fall off like this. This will fall off like this. The exponential fall off here is exponential minus alpha 2 x, and here is like alpha 1 x. Alpha 1 is equal to alpha 2 modulus of epsilon m. So epsilon m, please recognize, is the conductivity, epsilon m, effective permittivity, which is epsilon r minus omega p square upon omega square. So depending on the value of omega, if omega is very small as compared to omega p, epsilon m could be very large, and at those frequencies, low frequencies, the field will decay very rapidly inside the conductor, and what you can see here is that alpha 1 could be of the order of c upon omega p for omega much less than omega p. So the wave is really localized inside the conductor, very close to the surface, but it can have a broader width in free space. This is one important aspect of this. Ex one can similarly deduce and see the character. Now its applications, I would like to mention 3 very important applications of this wave. One was obviously for medium frequency communication. Earth is not really a conductor of the form like gold or silver. It contains soils, but when you are talking of frequencies like medium frequency waves or medium waves, we are talking about frequencies omega upon 2 pi in the range 300 kilohertz to 3 megahertz. So though the soil has soil particles separated from each other, or soil grains separated from each other by certain distance or maybe connected to each other, but the wavelength of this wave is very large, and consequently one can treat this to be continuous medium. So there may be pebbles, there may be clay, there may be water molecules, etc. But you can average out the properties of the earth. Typically, earth epsilon m for the earth at these frequencies is epsilon r plus I sigma upon omega epsilon 0. You may recognize that sigma epsilon r is like 4 for the soil, and conductivity is like 1 in MKS units. For wet soil this can go up to 10, so it varies between 1 and 10, but omega we are talking about 3 into 10 to the power 7 or 10 to, of the order of 10 to 7 radian per second. Epsilon 0 is about 10 to minus 11. So now you can recognize that this quantity is 10 to minus 11. This is like 10 to the power 7. So still this product is of the order of 10 to minus 4, and hence this is of the order of 10 to the power 4 times I. Means the imaginary part is much bigger than the real part, and you can ignore this part. And that helps you simplify the expression for propagation constant a great deal. So when we are talking of medium frequency communication over the earth, kz of this wave is equal to omega by c, and it was epsilon m upon 1 plus epsilon m. My suggestion is take plus 1 here and subtract minus 1 here, and then divide this quantity by 1 plus epsilon m. So you will get omega by c into 1 for this ratio minus 1 upon 1 plus epsilon m to the half. But epsilon m is very large magnitude wise as compared to unity, so you can ignore this one. So this is approximately equal to omega by c into 1 minus 1 upon 2 epsilon m. And if I put the value of epsilon m that I had derived just in the last sheet as I sigma upon omega epsilon 0, then this becomes is equal to omega by c 1 plus I omega epsilon 0 upon 2 sigma. Please recognize that kz is a real part which is equal to omega by c plus the imaginary part which is omega square epsilon 0 upon 2 sigma c. So this is strongly dependent on frequency, the absorption coefficient. Imaginary part of kz is called absorption coefficient, and this scale says, so kz imaginary part goes as omega square. That is why above 3 megahertz frequency, when short wave regime starts, the damping becomes so severe that these waves cannot be, the surface waves cannot travel long distances, and hence surface waves are not preferred or not excited in at that frequency band. But for medium frequency communication, when omega is low enough, these waves can travel. Kzi turns out to be of the order of 1,000 kilometers. And hence these waves can be used for communication from Delhi to Bombay, Delhi to even farther distances, even Soviet Union. People have recorded these waves. So that is a very interesting aspect of it, and as I mentioned to you, these waves can travel along the surface of the earth even if the earth's surface is curved. So they can go beyond the line of sight, geometrical line of sight, and that is the beauty of these waves. They also suffer little diffraction divergence. Second application that I wanted to mention is sensor application, for which excitation of surface waves over silver interface, silver vacuum interface is considered to be very useful. But a very special geometry is used called ATR configuration, called attenuated total reflection configuration. Let me tell you what is this. One chooses a prism and you deposit a silver film over this, like this. This is a glass prism of refractive index eta g, glass. This is metal, typically silver. Sometimes people use gold also. And you want to generate a surface, this is free space here. A very fascinating experiment was conducted, that you launch a laser here at some angle, say theta I. This is a metal with plasma frequency bigger than the laser frequency omega. You are launching a laser, simple laser, and then this will be a reflected wave here that is coming out, because this is a medium which is overdense for the laser, and this is like overdense plasma. It does not penetrate that much, but there will be some tunneling. A little bit of energy goes from here to here, but very little. And what happens suddenly if I plot the reflectivity, means the amplitude of the reflected wave as compared to the amplitude of the incident wave, square of that. So intensity reflectivity if I plot as a function of theta I, what I find, when this is launched at different angle of incidence, the reflectivity, suppose is reflectivity of silver for the laser is nearly 98% or so. So very close to the 1. But suddenly what you find here, that there is a dip here. At about 45 degrees angle of incidence, well, depending on the material, for gold it is 45 degrees, for silver it is just close, a few degrees away. But this is very sharp, and this reflectivity reduction could be like 70% reduction or so. So this could be like 0.3. That is something very interesting over here. And when does it occur? People wanted to match that what is the propagation constant of this wave in the glass. If omega is the frequency, omega by c, eta g is the propagation constant of laser in glass. If you resolve its components, vertical component of this propagation constant and a horizontal component, so then the horizontal component would be sin theta I. This is the propagation constant of laser in glass, its horizontal component. I am choosing this as my z direction, this is my x direction, and x equal to 0 is the top surface of the metal. And what has been found, that the value of theta I for which this occurs, this resonance occurs, let me call this angle as theta r. This occurs when this is equal to kz of the surface wave, surface plasma wave, which was equal to omega by c epsilon m upon 1 plus epsilon m to the power half. Something very spectacular occurs when the horizontal component of laser wave vector in the glass equals the wave vector of the surface plasma wave. Then there is a severe reduction. It means there is a conversion of laser energy into surface plasma wave energy, and the wave propagates near the upper surface of the thin foil. That is the called attenuated total reflection configuration. In brief, this is called ATR configuration. Otherwise, you were expecting total internal reflection of wave, but suddenly you found that there is a penetration of energy from here to the upper layer, and at the upper layer a surface plasma wave excited. Now, if you put little bit of material on the top surface like DNA molecule or a small layer of some dielectric material, then people found there is a significant shift in the resonant frequency, and that depends on the permittivity of the material that you put over here. So, just by observing the shift in frequency, one can deduce the permittivity of the material used, and the permittivity is a characteristic of a material, and hence you can characterize what material was there, whether it is a DNA molecule or whatever. So, the properties of dielectric properties or at optical frequencies can be gauged by this technique with great sensitivity. This has been one of the most sensitive techniques for diagnostics of DNA or diagnostics of undesirable gases in air. So, for this is essentially a sensor application, very useful sensor application. Let me also tell you something, one more application of this, which is in laser ablation of materials. Before I tell you something about the role of surface plasma wave in ablation of materials, let me tell you something about direct ablation of material by a laser. Suppose I choose a material, say gold, I want to deposit on some material here. Suppose this is my glass substrate called substrate. This is my gold. I want to deposit, suppose, gold film over glass. What if I do? I shine laser light here, directly here. What the laser will do? If the plasma frequency of the material is bigger than the laser frequency, the laser will not penetrate much. It will penetrate only up to a skin layer. This is called skin layer of width C upon omega p, very little. But the advantage of the laser is that suppose I have sent a pulsed laser of 1 picosecond duration, what would it do? Quickly it will heat the skin layer, the material in the skin. The electrons are heated by the laser, and then they collide with the lattice and transfer their energy to the lattice atoms, and the lattice melts, evaporates. Sometimes plasma is formed, a plume is formed, and that plume rises, and the plasma moves like this. A plume is created here, that goes up and strikes the substrate, which is kept at a low temperature. So, this cools down there, and a gold film is deposited on the top. Now, the thing is that if you are shining a laser, you are primarily utilizing or using the heating only in this region where the laser spot is there. So, your heating is very localized in the horizontal plane of the gold surface. And secondly, the heating rate depends on the laser intensity, so it is limited by the laser intensity. If you do not have a very, very powerful laser, then the heating rate is slow, and it may not, the heat that is generated here can be thermally conducted out downwards. So either you should choose a very large intensity laser, and you should choose a larger cross sectional area of the laser shining the gold surface, then you can deposit a large surface area film. However, what the surface wave does? It does an interesting thing. If I choose a material like this in the ATR configuration, the laser light that you are shining is only of this cross sectional. This is the cross section of the laser. Suppose the radius is R0, so 2R0 is the width of the laser. But when this laser gets converted to surface plasma wave, then the width becomes very narrow. This width is very narrow. The width of a surface plasma wave is less than a micron. The size of the laser is about 100 micron. So you are shining a 100 micron laser over a surface, and the surface wave is traveling over a very large distance, but localized in a very small region. So the laser energy that was spread over a width 2R0, that was spread over a width 2R0, means of the order of 100 micron or so, is localized in the SPW, surface plasma, over a width of the C by omega p, and that is the advantage. This is of the order of less than 1 micron, this is bigger than say 20 micron or maybe 200 micron or something. So there is a sharp reduction in the extent over which the laser energy is localized, and that leads to enhancement in amplitude. So there is a amplitude enhancement of this order, divide by this. So amplitude enhancement factor is 2R0 divided by C upon omega p, and this could be like 100, 50, 100 or whatever. Means equivalently you will gain the same effect here as if the laser intensity were to be enhanced in this case by square of this quantity. So you have got orders of magnitude and reduction in laser intensity to gain the same heating effect, and moreover this is travelling a long way. So this laser energy, though localized in the transverse direction, but horizontally is travelling a long way. So it can illuminate or heat the surface area several times more. Like here it was like 20 micron or so or 100 micron, this can spread over a distance of the order of 1000 micron or more, and hence a much bigger area is exposed and heating will take, ablation will take place. This is much more effective. That is a great advantage of this technique, means convert the laser into a surface plasma wave and let the surface plasma wave do the heating and ablation of material. I think that is a very interesting application of surface plasma wave. Finally, I would like to tell you one more application of this in material processing, by plasma processing of materials. What people in Taiwan have done, they take here a gas where they want to form a plasma, and then they create a surface, a structure, slow wave structure here. and they launch an electromagnetic wave here. What they find that if some plasma is created here, then this sort of slow wave structure excites a surface wave here, and that can sustain the hot plasma here. Means this electromagnetic wave field will initially cause the initial ionization, but that ionization, as it develops, there is a sharp boundary between plasma and free space, and then you will produce a surface wave. So when the electromagnetic wave gets converted into surface plasma wave, it becomes more effective in heating and sustaining the plasma. So this is utilized, SPW is utilized in producing plasmas for material processing. And I think that is a great advantage. So surface plasma wave is really emerging as a strong contender or a strong candidate for material processing, either via plasma route or through laser ablation technique, and it's also finding many device applications. I think I'd like to stop at this point. Thank you very much.